Okay, so let's talk about indeterminate structures, how we go about figuring out how to do these. So the problem with indeterminate structures is basically these are structures where we've got too many unknowns in order to allow us to use just the sum of force and sum of moment equations in order to find all the unknowns. So we're going to have to use some other compatibility conditions which match our situations. So sometimes this will be like known displacements or strains. One example that comes up quite often is going to be zero displacement at the supports. Could have known slopes. So if you have a support that's fixed at one end, then you know that the slope there at that end is going to be zero. You can make use of symmetry. So if the situation you're dealing with is symmetrical, then you can know what the you know how some of those reactions could be related to one another. They could be equal if they're just on opposite sides, and so on and so forth of the symmetry. So, for example, if you have a table with four legs, and you place a weight on the middle of the table, then just using the equilibrium equations, that's too many unknowns for us to be able to solve that problem. But if we make use of symmetry, then we know that since everything is symmetrical about those two axes, we know that the reaction forces at each of the legs of the table is going to be equal. Therefore, we can just assume that the reactions there is equal to the weight of the weight plus the weight of the table divided by 4. We can have like equal unknown loads in some cases. Equal unknown loads, equal unknown strains across various segments of the problem in question. So, like for example, for equal unknown strains, a good example would be a carbon fiber composite. So when you're figuring out how the carbon fiber composite reacts, actually, that kind of works for both of those. If you're pulling along the direction of the fiber, then basically you've got the matrix material that latches on, that's bonded to the fibers that are kind of providing the structural support. So those have basically that causes the matrix material and the fibers to have equal strains. We don't know what that strain is, but we know what they are relative to one another. They're equal. If you push on it downwards, say for example, or from the side, whatever. If you push on it in a direction that's perpendicular to the direction of the fibers, kind of works the other way, because then essentially you're not oriented in the direction of the fibers, so the strain isn't necessarily going to be equal. So in that direction, basically we treat it as if the stress level is equal throughout the entire structure. And of course, some node loads could help us figure that out. So oftentimes, a technique that will need to be used will be basically we can take one of the reactions at the support and treat them as a redundant load, and then kind of compare that as if we had the and then compare it to like known situations. So the example that we got here, we've got this sucker here where we have a support in the middle, and normally, you know, if we had the distributed load pushing down, we already know basically that problem's already been solved. So we can look up how it deflects in a table, or we could do it the old-fashioned way if we really want to. But okay, so I could do it the old-fashioned way if we really want to. You guys haven't gotten to that point yet, but yeah, that's a bit beside the point. So we know how that one would react if this load wasn't here, and we also know how this this beam would react if we just had a force pushing up in the middle. So basically, we just kind of take those two scenarios, the distributed load without the support in the middle and something pushing up in the middle. And our compatibility condition here is that the displacement in the middle there needs to be zero, because that's what the support does. The support is there to ensure that the displacement is zero in the middle, despite whatever else is going on around it. So essentially, we take this displacement caused by the that would otherwise be caused by the downward displacement from the distributed load, and the force upwards at the reaction needs to be enough that that if it was just applied to the beam itself, it would push it up that same amount. It would push it up enough that its displacement, that the total displacement is zero. Now, of course, that's total displacement that needs to be zero at that point, based upon this distributed load. You could add other loads here as well, other loads corresponding to other known scenarios. Like, I don't know, you could add say you could add a moment here that's kind of bending the beam down a bit, and that would cause an additional bit of displacement in the middle, and that would act to increase the amount of the reaction force needed in order to maintain our zero displacement compatibility condition in the middle. So you always need to find and state compatibility conditions which make sense for your scenario. So some of these, like when we're talking beams, we have these beam bounding formulae, and I got a PDF kind of listing these posted to Moodle. There's equivalent formulas in different textbooks. I found this one from this textbook by Pytel and Q. Salas. I think that it's the best formatted of all the ones I was able to find. But again, if you want to use a different one that you like better, just be sure to identify where you're getting this information from when you use it. So again, we got a number of known cases. So we know how much a beam is going to displace downwards when you press down on the end of it, and that'll be a function of how much the load is, where along the length of the beam you are, what the modulus of elasticity for the material is, and what our I value is there. So typically, we're given the displacement kind of as a function of x, and they also tell you kind of the displacements in the extreme cases. So the end of the beam in this instance as well. We've got the angles at the end. So got that for cantilever beams. We got this also for simply supported beams, supported on both ends with a pin joint, except of course, conceptually speaking, they'd simplify it by treating the one end as kind of a pinned roller, so it's able to move back and forth a little bit. And that's kind of just to simplify the math a little bit so that we don't need to worry about how much the beam is stretching kind of axially as we do this. If you do actually have it kind of pinned on both ends, there will be some stretching, but typically speaking, it's relatively negligible. It's really the vertical displacements that kind of come up a lot. So, yeah, other scenarios you can use. Again, just pick the known scenarios that correspond to the situation that you're trying to model. And then there's a few others I found in this Budnies textbook that are also useful. So distributed load with cantilever beam on one end and a simple support on the other, or a cantilever beam on both ends with a load in the middle, or a cantilever beam with fixed supports on both ends and a distributed load in the middle. So yeah, when it comes to solving your indeterminate problems, again, cannot reiterate this enough. You just need to find a good compatibility condition, state it, set up your system of equations, and the compatibility conditions are going to be what allows you to relate the various unknowns that you otherwise wouldn't be able to solve for in a manner that reduces the problem to something that's solvable. So that's it in general, and we'll go through a few examples.